Good afternoon. It's right after lunch, so you'll see I'm a little informal. I'll even have a joke in the beginning. I like to kind of get things going here. I'll be the moderator today. We have some awesome panelists, and I think we're going to have some really good discussion. My name is Darrell Phillipson. I'm the director of the Materials and Manufacturing Directorate at the Air Force Research Lab. I am actually very honored to be here and be able to chair this panel today. So before I get going, I said I do have a little joke, but actually it's a little bit of an audience participation. I can hear the groaning already, but it's going to be super easy audience participation. So I'm going to ask two questions. You got to raise your hand for one question or the other. So most people are either a Marvel Universe fan or a DC Comics Universe fan. And if you're not, just pick one, because everybody has to raise your hand once. So, DC Comics? Ooh, that's not too many there. I like Superman, so I got to go with them. Marvel? All right, good. The reason I bring that up is because sometimes you have a pretty temper between those two communities. And recently, I heard that actually Superman is going to be teaming up with the Silver Surfer, and they're going to be coming out with a new movie. Has anybody heard that? So cross-universe, yeah, apparently they're alloys. All right, come on. That's as good as I got, all right? It's a materials joke. All right, so I am excited to be here. Aerospace industry stands, in my opinion, at the intersection of innovation and urgency. Designing for the production system, focusing on speed, efficiency, and scalability. Scalability is super important. It's never been more critical than today. The subject is actually particularly vital for the Department of the Air Force, and that's why I was excited to chair this panel today. And it aligns very well with my particular job. I'm as I said, the director for the Materials and Manufacturing Directorate. We're charged with developing materials, not just the materials, but the manufacturing processes that provide our warfighters with unmatched capabilities. That's unmatched capabilities delivering technology at the cutting edge. However, it's critical that we do that in a scalable way, that's reliable and cost effective. It's just not always the state of the art now. We have to be able to manufacture, we have to be able to build, we have to be able to scale to meet our customers' needs. One of our key priorities is accelerating transition from research to operational use within the Air Force Research Lab. And this session is going to be focusing on a few areas that I think are challenging, not just for the research lab, but probably for the entire community. And that's the need for rapid qualification, scalable manufacturing at speed, and leveraging and figuring out how to leverage technologies like artificial intelligence and robotics. So I've kind of expressed why I'm excited to be here. You all are here to hear this session, so hopefully this resonates a bit with you all. And as the panel chair, I think that's about as much as you need to hear from me. So I've been delighted to introduce our esteemed panelists. I'll go through a quick introduction. Mr. Trevor Campbell here, he's the Industrial Microscopy Product Manager at ZEISS Industry Quality Solutions, and he'll bring some insights into materials innovation and quality improvements. Mr. Jay Douglas is the COO of the Advanced Robotics and Manufacturing Institute, the ARM Institute. He'll be sharing how robotics and automation can accelerate aerospace production. Ms. Karen Taminger is a senior materials research engineer at NASA Langley Research Center, and she'll be offering some expertise on material challenges and opportunities in green aviation and next generation vehicles. And Dr. Dazhong Wu is the assistant professor at the University of Central Florida, and his focus is primarily on additive manufacturing and AI-driven material design. How we'll run the panel today is each of the panelists will first just give a little bit of a background highlighting, or a little bit of an introduction, highlighting their background and a couple of perspectives. No slides, just ideas, insights to kick off the session. Then we'll go into some prepared questions where I'll delve into three primary areas. That's how we'll structure the time here. overcoming challenges in certification and quality, accelerating production for aerospace needs, and equipping the workforce for future manufacturing. Then after that, I think there's a way for our folks to submit questions. So if any of this conversation sparks some questions that you have for us, please jump on there, add your questions, rank other people's questions so that we can kind of try to address the highest priority questions or the things that are most pressing on your minds near the end, and then we'll go around robin at the very end for a wrap up. So without further ado, if we can kind of start left to right here, and if you can highlight a little bit of your background, introduce yourselves, and some perspectives. Over to you, sir.
Sure. My name is Trevor Campbell. As Darrell mentioned, I'm the Industrial Microscopy Product Manager at ZEISS Industrial Quality Solutions. I'm also our Aerospace Solutions Manager, so I lead a team of about 10 to 12 people who are focused on the aerospace industry and how we can support those customers. My background is in industrial microscopy. I've been in the industry for about 15 years now, doing everything from sales and applications to product management. And I've seen a lot of evolution over the last decade or so that has really advanced materials analysis and enabled it to be a lot faster for meeting the needs of advanced manufacturing and new innovations in materials development, things like additive manufacturing, which has really taken off in the last 10 years, and then advanced materials characterization through our software, which will help make things a lot faster too, particularly through innovations in artificial intelligence and image analysis. So I want to talk a little bit about that today and how automating your inspection process, particularly through light and electron microscopy, is making it so that you can improve not just the analysis of the materials, but the manufacturing of it, because it becomes a lot easier to check things nearly in process, where you can take a sample, analyze it very quickly, and tweak things, whether it's something in additive manufacturing, where maybe you need to change the printing properties to change the material qualities, or something in casting, anything along those lines. So I'll delve into that a little bit today and talk about how the inspection side of things is making it a lot easier to improve materials and check quality faster.
Jay?
Okay, thank you. My name's Jay Douglas. I'm the Chief Operating Officer at the Advanced Robotics for Manufacturing Institute. We're located in Pittsburgh, Pennsylvania, on part of the campus of Carnegie Mellon University. Our 8th birthday is on Monday next week. So, we're not brand new, but we're still pretty new. Our mission is to improve U.S. manufacturing competitiveness and thereby national defense through the use of robotics. So how we do that is we initially started to raise a consortium, an ecosystem of companies, universities, startups, big aerospace companies. We now that ecosystem numbers about 475 organizations. We are sponsored by the Manufacturing USA organization within OSD. We work with our sponsors in the government and our advisory board to come up with problem statements that, if solved or created, could help solve these problems we're working on, manufacturing competitive national security. So we publish problem statements and invite our members to give us proposals that we evaluate competitively. Then we fund them. We've run over 150 projects to date. At the end of the project, the result, the intellectual property, is shared across the consortium, either for use or for continued development. And that's how we're doing what we can to impact. We've already seen about 75 different instances of transition. So we're pretty pleased by that. We also work in the areas of the workforce problems with advanced manufacturing. As far as the topic of today is concerned, I know that robots do a great job in speeding up manufacturing in many areas, not in all. Robots typically can't do what people think they can do, but they can probably do what you never thought of. So that's a big thing. They also don't take vacations. get sick or walk away from their job very easily. So another way that speed is enhanced. So more on this later. Thank you.
All right, Karen?
I'm Karen Taminger. I'm at NASA Langley Research Center in Hampton, Virginia. I started working there 2 weeks before the Challenger accident, so that, if you know your history, dates me. So we started working wire additive manufacturing back when it was called solid freeform fabrication more than 20 years ago. And so we look at developing technologies. We don't build vehicles, but we enable them. And so the materials, the manufacturing, the work that we do, it looks to try to look to the future at what potential needs are going to be, what the environments that those vehicles are going to be asked to operate in, and then look at what materials, manufacturing methods are compatible with those end applications, and then trying to get out ahead of industry to develop those long-term promising technologies that might be something that in 20, 30 years you'll actually see in vehicles. And so although a 20-year timeline for development doesn't seem like a short time, industry is just now starting to really get serious about additive manufacturing. So that past 20 years, kind of builds up into that. So we've got a couple of different projects that we've worked. We've done a lot of collaboration on the Advanced Composites project and the HiCam project, specifically looking at rate-enabling technologies for commercial transports for composite manufacturing. And so in that project, we do a lot of collaboration and work on what are the manufacturing methods and the technologies around that, the computer-based, the model-based engineering and the integrated sensors. What are the things that can help to increase the rate of production of aircraft? We also, in some of our other research projects, we're looking more at what those end applications are. And so the Advanced Air Transport Technology project that I work in, we looked at toe steering of composites for combining aeroelastic tailoring and stiffness to reduce the weight and improve the performance of very high aspect ratio wings. And so again, things that we're starting to see looking as a potential. And so we'll do the technology development, the computational and the experimental, looking at the manufacturing, the materials, and that whole ecosystem, and how do we demonstrate things early on so that those can be matured and adapted and adopted into future vehicles. The other thing is that we work on both air and space, and so one of the other technology areas that we've looked at is launch vehicles, and how can we make launch vehicles quickly and cheaply, looking at, instead of large-scale assembly of components to make cylinders, building cylinders as an integrated unit. And so recently we took things that we learned from the space side of the house and brought that into the aeronautics side and looked at, how can we build a single-piece fuselage in an hour and a half with integrated stiffeners, eliminating hundreds of thousands of rivets and the time associated with installation, as well as the damage tolerance that concerns with all of those holes and rivets. And so looking just at what are the things that we can do and develop that can then be transferred to those technologies, but also understanding the technologies to enable more rapid certification when industry is ready for them.
Excellent, thank you. Dr. Wu?
My name is Dazhong Wu. I joined UCF, University of Central Florida in Orlando. I'm local, about 7 years ago. So my research lab had three different research thrusts. The first one is additive manufacturing of polymers, fiber-reinforced composites, ceramics, as well as alloys. So the second one is about AI or machine learning-enabled smart manufacturing, where we leverage AI or machine learning algorithms to make manufacturing processes more intelligent, try to detect defects in manufacturing processes, achieve near zero defects in manufacturing. And then the third research area is about prognosis and health management, also known as predictive maintenance, where we also utilize machine learning AI to predict remaining useful life of almost all mechanical components, from simple components such as bearings, gearboxes, battery systems, until the most complicated systems such as jet engines.
All right, thank you. So we're going to kind of direct each of these questions to one of the panel members, but invite any of the panel members if there's a follow-up or anything that you'd like to share on any of the questions that we'll just kind of do a little bit of free flow as we go through the questions. So Dr. Wu, you got to go last, and I'll give you the easiest question of all, which is not easy at all. So from your perspective, what do you see the challenges in part qualification and certification for additive manufacturing? Pretty big question.
Okay, so I guess so this topic is very relevant to one of my research areas. So I think part qualification and certification probably are $1 billion problems to solve. Not million, but $1 billion industry. So especially for aerospace industry, probably this is one of the most challenging issues to solve in order for aerospace industry or companies to actually adopt 3D printing. Particularly, probably we are talking about most likely composite printing as well as metal 3D printing. And the reason why this is a really challenging problem is because it's very complicated. So for example, if we talk about part qualification and certification, I guess we are talking about two aspects. Number one is printing quality. Specifically, we are talking about defects. And the number two, second aspect is about overall performance of 3D printed parts. In other words, the mechanical properties, such as tensile strength, fatigue strength, Young's modulus, yield strength, compressive strength, resistance, all those critical mechanical properties. I guess both printing quality and overall performance, they are correlated. Oftentimes, overall performance depends on printing quality, especially depends on microstructures of 3D printed parts, as well as defects, such as porosity. And this is one of the critical issues. And then when we talk about both, I guess let's maybe talk about specifically two areas, starting from raw materials. So I guess if we want to really qualify parts, we want to start with qualification of the raw materials. In this case, let's talk about metal powders, if we're talking about metal 3D printing. So if you're familiar with metal 3D printing, so if you are a material scientist, so you probably think that this is a very important, interesting problem to solve. And I will give you some examples. So let's say if you purchase an order from some metal powder vendor, so and then you print your parts using this batch of this powder. And then 1 month later, you place another order from the same vendor, the same geometry, the same CAD model, almost the same processing conditions. And then you will find out the parts from these two batch of raw powders will end up with different mechanical properties, behaviors. And this is one of the critical issues, right? Because you want to make sure so your parts have a consistent mechanical behaviors. And then this is one of the first reasons we need to issues we need to really qualify the part by qualifying the raw materials, which is metal powders first. And this is very challenging because the overall performance and the printing quality depends on many factors of the raw materials, which is metal powders, such as the size distributions, also the shape distributions of the metal particles. And I said before, so even you order these or purchase these metal powders from the same vendor, but the quality of the powders will change, will vary, depending on which batch you are using. And there are lots of uncertainties associated with the raw powders. And then once you have the raw powder, okay, the second issue we need to control in order to qualify a part is to control manufacturing processes themselves. So regarding the second aspect, I think there are some critical issues, especially, I will also give you one example. So let's say you have the same parts, the same CAD model, but you print the same part using two different metal printers developed by two different vendors, let's say EOS or SLS Solutions. And then you will find out, oh, these two parts, the same geometry, same CAD model, same material, may end up with also different mechanical behaviors. So this is the second challenging issue That's why qualification and certification is so important and also difficult. So there are some solutions to both problems. So for example, in order to qualify metal powders or raw materials, people have been using all kinds of microscopies. Right? For example, in my opinion, one of the probably most cost-effective way and also efficient way probably is to use a micro CT scanning. So you can use micro CT scanners and to scan the raw powders in order to characterize the performance or the quality of the raw powders. And oftentimes, those high-resolution micro CT scanners can achieve maybe 3 to 5 micron resolution, which allows you to see those or observe those metal particles very clearly. And some of the solutions to the second aspect, which is control the processes, people can build high-fidelity simulation models using FEA or CFD. People can also use in situ monitoring. And I think the second one probably is most promising, where you can use actually all kinds of sensors, let's say thermal cameras, even light cameras, and also all kinds of temperature sensors to monitor metal printing process in real time, and then use machine learning or AI techniques to analyze those data to identify certain patterns, and also analyze or reveal certain relationship or correlation in the data so that you can control the process and also control the mechanical behavior of 3D printed parts. I think that's my brief insight to the first question.
Yeah, powder inspection is a huge part of the additive industry, and microscopy plays a pretty large role in it, both from looking at the size and morphology of the powders and also the elemental composition. Was there any variance in the actual composition of that metal? Are you getting the same exact alloy every time batch to batch, or is there some slight variation that is causing some kind of issue with behavior in the finished part? Not only that, you talk about variance between the printers. Maybe one is making different pore sizes than the other. If you're intentionally leaving an open structure in your prints, are you getting the same pore shapes? Are you getting irregular pores where that's inconsistent and that's leading to weak spots that's creating fracture sites and some kind of deformation failure in the component? So you may even need to get into something like CT or X-ray scanning to actually look at those pores in slices and look at the shape of them. Are they a keyhole structure, or is it a lack of fusion where you've got some sharper points and you're creating stress areas that are going to lead to a fracture?
So a thought that I have, I think back 40 years ago, 30 years ago, at the beginning of composite material introduction, how are we going to certify this? And the challenge is the materials are being processed in a distributed fashion rather than at a mill where the material is qualified. And additive manufacturing has a lot of similarities to that. You know, your individual manufacturing processes are now happening all over the place, not in single controlled places where they've got material certs and that. And one of the solutions that NASA and the FAA helped to develop at NIAR on composite materials is a pedigree database where people can submit composite materials for testing, and then that is compared against the whole database of all of the other material properties from all the other composites, and they get flight certification to be able to use that composite. And I think that this may be a really good opportunity to learn from other examples where we've been able to certify materials in the aerospace industry for additive, and find a way to protect the proprietary nature of those processing parameters, but still find a way that it can be shared and built into a broad-based database that would enable some of the statistical analyses that are really the key to that ultimate certification. So maybe an opportunity there to leverage an approach that's been proven to be successful.
That's awesome. Thank you. That's a meaty topic to kick off this section with. The section is overcoming challenges in certification and quality. So that's just for additive. I will make a plug, Dr. Benedict, if you can raise your hand. Dr. Mark Benedict is here from the Air Force Research Lab, and he's our senior scientist that's really kind of tackling this for us. So feel free to follow up with him as well. If I can change the topic a little bit, Trevor, when it comes to aerospace materials, how do you see artificial intelligence improving innovation and the quality of the materials themselves?
AI has been a big factor when it comes to materials improvement, materials analysis. On the analysis side, it's really created new ways to be more repeatable when it comes to inspecting the same materials and able to do it a lot faster. Traditional image segmentation for light or electron microscope images was based off of contrast, luminosity, and intensity of the pixels themselves, where you would separate areas to do things like grain analysis, porosity, multi-phase analysis. But more modern materials have become more and more complex, and there's a lot more nuance to what those images look like. Very fine differences in contrast that a traditional contrast-based histogram isn't going to be able to pick up. Using artificial intelligence, we can train it based off of images that we've acquired, where you're going in and teaching it what these different variances are, and it can look at a much higher amount of characteristics, up to 256 characteristics beyond just contrast and luminosity, where it can discern either very fine differences in contrast or color that maybe you can barely detect with the eye and a computer would have a hard time with traditionally. But it can also segment things that are compounds. Say if you were to cross-section something like a battery, looking at the difference between the foils and the powders and the catalysts and all of that, and the electrode and cathode, you can basically tell it what a pattern is, where it can actually segment that pattern as one region of interest rather than individual ones, which is what a more traditional segmentation base would do. So you can train it to detect things that are a lot more challenging than they used to be. So many of those types of materials were a lot more difficult to detect and classify in the past because you really couldn't automate it. You had to go in and kind of manually either draw things and try to show it what something was and do a very rough calculation. So if you were trying to meet that speed demand of manufacturing, it was hard to achieve. It was going to be a very slow process. It was going to take you a long amount of time to do one sample because you were doing almost all of the analysis yourself. You were going in and selecting things and adding and adding and adding until you were happy with that region, or you were doing a very small region of interest and extrapolating, which, depending on your sample, may or may not be homogeneous throughout the whole sample. So you could be taking a real non-representative region and you're mischaracterizing the sample. Using that AI, we can automate a lot of that and make it a lot easier to do much larger areas. So we can take, like, for instance, a very large tiled image of an entire cross-section of that sample and then let the computer run the algorithm and segment it and do the analysis for you. So much more accurate data because we can analyze larger regions of interest faster, and much more automated segmentation because we can train the models to detect it for us.
Okay. So, thank you. Thank you. We'll shift now to kind of the production rate. Karen, you got me going in the beginning where you talked about aging yourself, and I realized, I thought you were going to say rapid prototyping, because in the 90s
Oh, solid freeform fabrication.
it wasn't even that yet, so it was rapid prototyping. So age myself as well. So Karen, if you can share with us some of your thoughts on the areas of manufacturing that offer some of the greatest opportunities for increased manufacturing rates for aviation.
Yeah, so manufacturing rates, you have to look at, we tend to focus on the processing of a component because as materials and manufacturers, that tends to be where our headspace is. We really have to take a step back and look at the individual component to the full assembly of a vehicle and understand that one component may not be the longest time. And so assemblies, building larger integrated structures, is one opportunity that allows you to accelerate your overall manufacturing rate because you've got fewer pieces that you need to track and you need to put together. One of the requirements that you need to do then is that you need to have close monitoring and integrated non-destructive evaluation to make sure that as you're going along building that assembly as a single piece unit, that it's going to serve its function, because you've got a lot more invested in that one part then. Interesting, I'm a materials scientist, and so my idea of adding cameras and sensors into something like an additive process is for me, I'm watching what's happening at the point of deposition, the point of fabrication. Working with our non-destructive evaluation folks, they were looking at other parts of the structure, exact same sensor, same data set, they're looking at other parts of the data set, and so they said, you got a crack that started way down here. And so the multidisciplinary, bringing together those different technologists, the different areas, helps to improve the quality as you're building, but then it also looking towards integrating inspection while you're doing that fabrication, while you're building those components as single piece assemblies rather than multi-piece assemblies, gives you the opportunity to attack many pieces of that overall manufacturing process at the same time.
Excellent. Any other thoughts from the panelists? No? Okay. Well, let me shift to you, Jay. From your perspective, what are some of the unique materials and manufacturing challenges? Oops, I'm sorry. It's the wrong question, Jay. All right.
I hope so.
Examples? Give me some examples of how manufacturing innovation institutes can accelerate the development and use of innovative solutions, and maybe you can share with us a little bit of the value of the public-private partnerships that are available.
Yeah, so that's what we do, public-private partnership. We have money from the Department of Defense that we invest in projects that are worked on by a variety of people from the economy. Startups, big companies, universities. We can put a really unique project team to work very, very quickly. 2 or 3 startups working with MIT and Lockheed, all trying to solve a problem. We've had projects with Lockheed and Boeing because we're a pre-competitive consortium. We can bring people to bear like that. We can also bring non-standard organizations in to solve logistics problems. We've had FedEx as a member since our start to help work on things like that. So that's one of the benefits. One of the greatest benefits, though, is we put together a set of processes where we can move very, very quickly. In the summer of 2020, not 2020, COVID summer, if you remember, we published a project call, and 45 days later had money on contract. Now, that's like ridiculously fast, but we can do that because of the way we organized ourselves. It's not just a fast, manufacturing process. It's a very fast process of getting solutions done. We've also been, we've been successful at demonstrating, maybe not for full production, but demonstrating things that can be done to accelerate processes. We've done a lot of things in the aircraft sustainment business, removing and putting on paint, countersinking and removing, rivet holes, things like that very quickly. Robots, artificial intelligence robots do things in the inspection space really, really well. They don't make a lot of mistakes and they don't take breaks. But we've also worked in some spaces where, so what does it matter to national defense that we have a robot that sorts fish? Well, it's an interesting example, is we have a robot that can tell the species, the sex, the weight, and the freshness of a fish. And so we have the ability to do things like that that could potentially translate into other areas. And I think that's the value of the Manufacturing Innovation Institutes. We happen to focus in robotics. There is one in additive, and there's 17 other ones across the United States working in a variety of ways. So that's a quick summary of some of the ways that we can impact things on the speed side.
Awesome, thanks, Jay. Now, I think every brewery has like a special beer taster guy. Don't replace that.
Yeah, no, we're,
Got a job. See, I realize you all laugh more when I ask the wrong question to the wrong person than when I make a joke. God. All right, thanks, Jay. Karen, I'm going to jump back to you. What are some of the unique materials and manufacturing challenges facing emerging air vehicles beyond commercial and kind of the standard stuff when we talk to UAM, supersonic, hypersonic vehicles?
Yeah, so when we start talking, a lot of our life is in commercial transport because it's such a large part of the airspace. But when you start looking at the higher speed vehicles, the hypersonic vehicles, the end applications end up really needing to drive what materials and what materials you need. The shapes drive the manufacturing processes. And so some of these manufacturing processes that have been developed over the years may need to be adapted. So for more difficult to process materials, higher temperature materials are not as easily formed as aluminum. When you're starting to talk, and they're more expensive. And so trying to be very efficient in the manufacturing processes, some of the taking advantage of additive manufacturing, the ability to do a functional gradient where, you may be able to integrate the function of thermal control and structural in a single component and make adjustments to either the microstructure, the material properties, or the chemistries themselves using advanced manufacturing processes like additive. Advanced joining processes, we need to be cognizant of it's not a one-size-fits-all solution. It needs to be a very directed solution depending on what the need is for that, for these other missions. High-rate manufacturing for a hypersonic vehicle is very different from a UAM because the quantities are different. So learning from the automotive industry, are there ways that we can do stamping and forming of materials that are perfectly fine for a UAM that may not work for something that has people on it, for example. So it's really looking broad spectrum at what are the needs, and then how do you match the manufacturing processes to what those end applications are. There's many materials challenges out there, and the route to certification is very similar, but it's a long process. And so that's something that as we're selecting materials manufacturing processes, we need to have in the back of our mind, how is this going to manifest and be allowed to be used in the endpoint? And so all of those, there may be ways that we can learn from one system, use the same sensors, just adapt it for a different temperature, a different material, to be able to apply those and help broad spectrum, even though we've got different requirements.
Okay. Dr. Wu, if I can jump back to you for a question. How can artificial intelligence or machine learning accelerate materials design to achieve near zero defects in manufacturing, as well as predict mechanical properties?
Okay, so I guess this question has three aspects, right? I will talk about the first aspect, how people can leverage AI to do material design. So I'm not a material scientist, but I've seen studies where engineers and scientists have been using machine learning models to actually explore very large material design space. So let's take a high entropy alloy design as an example. So if you're familiar with high entropy alloy, so actually there's a huge, large design space for you to explore in order to achieve a certain desirable mechanical properties. And then actually this is one of the areas people have been using machine learning and demonstrated that machine learning are able to significantly accelerate the material exploration process. And then I want to more focus on actually structural design because I'm a mechanical engineer. So we have been developing machine learning models, building machine learning models to actually generate lightweight and strong materials inspired by nature principles such as honeycomb. So you have seen those lattice structures. Those are inspired by crystal structures in chemistry. But whatever bio principles we are talking about, so we have been developing machine learning models to actually inversely design particular lightweight and strong structures that exhibit the desirable mechanical properties. And oftentimes, if you do not utilize machine learning, so there are many parameters you can tune in order to actually achieve a certain desirable property. But you can definitely use a trial and error approach, which will be time consuming and very expensive, labor intensive. You potentially can still achieve end up with a similar design, a structured design with similar property. But what we can do is actually we are using something called generative AI, similar to what people have been talking about ChatGPT, but now we're using generative AI to reversely design a structure, basically by specifying a particular geometric parameters, some parameters of lattice structures, such as porosity, and also the dimension of a unit cell geometry. And then also generatively determine processing conditions. Because as I mentioned before, so your 3D printed parts, the performance depends not only on the geometry or the shape, but also processing conditions. Because processing conditions affect or introduce additional defects or will affect microstructures. So that's why oftentimes most of the software packages you are using can only generate one optimal design if you're using topology optimization. But if you use generative AI, it will generate hundreds or even thousands of structures with similar desirable properties. So it's different from a topology optimization. It's hard to say which one is better than the other. It really depends on your use case or your purpose. But this is one way to actually explore new materials using AI. The second aspect is to achieve near zero defects. So I already talked about this before. So actually you can use all kinds of in situ sensor data along with machine learning to predict porosity and also predict other defects such as warping, which is very common as well for large flat metal parts or composite parts. You can also predict distortion. And also probably more challenging part to predict is you can predict actually a residual stress of 3D printed parts, which is very challenging. It's even very difficult to really experimentally to characterize residual stress of 3D printed parts. The third aspect is how we can leverage AI to predict mechanical properties. So actually, I also have seen studies where people predict the entire stretching curves of 3D printed parts. So if you're still familiar with solid mechanics of mechanical properties, so you will know actually if you can generate a stretching curves or force displacement curves, then you can pretty much determine all mechanical properties, right? Such as Young's modulus, or ultimate tensile strength, or the area under the curve, which represent toughness, right? As long as you can generate those curves. But oftentimes, probably the most common practice in industry is to use destructive testing, right? You break apart using a mechanical testing frame, and then generate or collect those data, and then graph or plot those stretching curves. But what people can do using AI right now is to generate the entire curves using a relatively small experimental data. Of course, it is still training a machine learning model still require experimental data. So we will not totally eliminate destructive testing, but with relatively small data sets collecting from experiments, you are able to generate the entire curves. And more importantly, people have been using, at least our group has been developing something called transfer learning. Basically, a transfer learning algorithm allows you to transfer knowledge from one problem to a different but a similar problem. I will give you one example. So we actually conducted over 100 tensile tests, and then for one material, one polymer. And we are able to use these relatively small data sets and then generalize this transfer learning model to predict mechanical properties of a different polymer, although similar, but a different polymer. And then later on, we can generate even larger but relatively small data sets collecting from composites, and then transfer the purpose model, a generalized purpose model, and then apply to predict the mechanical behavior, the entire stretch curves of different composite materials. So now, although it's not very transformative, because I'm still talking about transferring knowledge between two polymers or between polymer and the composite, but in the future, I believe AI probably will allow you to transfer knowledge between a polymer and a metal, which I think is huge. We are working on this, but we are still collecting relatively large data sets because these two different materials are so different. But I think it's promising.
Thank you. Any others? Okay. Well, we're going to transition now into kind of some thoughts on workforce. If I can start with Jay, what innovations are there to aid DoD organizations in dealing with their workforce and supply challenges, or workforce supply challenges?
Well, there's a myriad of them out there. I can talk about what we've done. When you look at advanced manufacturing in the United States from a competitiveness perspective, what everybody talks about, the biggest problem is being able to hire a qualified workforce. And in the United States right now, there's two fundamental issues. One is a skills gap. The other is a supply problem. In the next 3 to 4 years, there could be as many as 5 to 6 million open advanced manufacturing jobs in the United States. January last year, I think the number that we had specifically was over 780,000 open positions in manufacturing. And the economists will tell you in the near term, you can't grow the economy unless you can put people to work. And one of the ways to generate a lot of GNP is through manufacturing. So we've created a capability. It's a website that we've deployed nationally, but also specifically in some areas that had more unique problems. But what it is it's a website that has 17,000 different training programs listed on it and the information behind those. We've defined 3 different job types in advanced manufacturing, particularly in the robotics space. And you can go onto this website as an aspiring manufacturing worker and see what job you might like and what skills you need to have that job. And you can then put in your zip code and it will come back and tell you where you can get that training near where you live. So it is a way to accelerate the connection between creating a skilled workforce and the jobs that are available in that area. The website also lists 6,000 different open jobs in advanced manufacturing, and we found that to be one effective tool. Most geographies have some sort of workforce initiative. It's a very popular thing with local governments. So I encourage everybody to look at where you live and what's available, or come to us. It's called roboticscareer.org, and it's available nationally. A little commercial there.
All right.
It's one example.
Thanks, Jay. Karen, how do you see, kind of from your NASA experience, workforce development playing in accelerating manufacturing innovation?
Yeah, so thinking about things like additive manufacturing, kids know how to additive manufacture, right? They've got 3D printers in schools, and so but their solution tends to be go to the additive manufacturing because that's what they know. And they haven't necessarily learned about all of the other realm of manufacturing, some of which are maybe better suited for a particular application. Right. And so it's making sure that, and the reverse is true. The folks that have been building things for years and years and years the same way may not have that exposure to what's new. And so it's that cross-training of what's old and what's new to multi-generations to make sure that they can draw from the whole body of manufacturing, because additive manufacturing is not the answer to everything. I know. But, and you know, it's funny, I was talking to somebody who was teaching additive manufacturing classes, and they had the students design and build a wrench. Design and built a wrench, no problem. They said, okay, now go use this. And they said, I don't know how to turn a wrench. They didn't know. It keeps falling off. It's a box wrench. And so it really is, it's that making sure that there's a broad-based training. The other gap that I see that really is going to need development is, and so maybe not for high rate, but for manufacturing in general, is the inspectors. Your inspectors, whether it's the FAA or our internal inspectors, need to understand the pros and the cons, the pitfalls of the manufacturing technologies. If they just believe what they read on the internet, they're not going to get the whole picture. And so they have to be able to see through the hype and understand where there are appropriate uses for different manufacturing processes. And I think only through that type of education, broad-based, as well as making sure that the inspectors who are making sure that things are done correctly are well-trained and versed in what correct means, is really what we need to do to advance adoption of any new technology. And the new technologies have the potential for increasing our manufacturing rate, but only if applied properly.
Yeah. Thanks, Karen. That's pretty startling as I hear didn't know how to use the wrench that they were designing. Like, oh.
I won't tell you which organization. Offline, I'll tell you which organization.
Might be mine. No. But that's a good point. It's that foundational knowledge as well. Of course, there's the other side of it. And Jay or Trevor, I'm wondering, can you share how can we train? Kind of the flip side, though, is on the emerging technologies like AI and additive to complement that core, but also in a way that moves us forward.
So that aspect sort of brings two sides to this, is that it's kind of adding to the workforce and the expansion of it in two ways. One, it's opening some higher level positions for people that are helping advance the AI aspect of it and trying to make it more intelligent and find ways for it to bring new value and speed to what people are doing. At that same time, the development of it has also enabled people to do some of this analysis a lot easier than they had been before. So someone doing some of these materials analyses might not necessarily need a high-level material analysis degree to be able to perform it. They just need to know how to run the model and look at the data. So they don't need to understand exactly what it's doing to be able to get the right numbers. So it is opening some more entry-level positions into the workforce where people can sit down in front of the instrument and just need to be trained on how to run the instrument, not necessarily how to understand what the material is doing. By doing it, they're going to gain that in a real-world knowledge, but getting started has never been easier because the technology to do that is so much more available and so much more intuitive than it once was, where someone was sitting down in front of an image and didn't know what they were looking at unless they were taught exactly what it was and how to understand what the different regions in the image meant and what the composition of it meant. But then there's also, again, that higher aspect where someone is developing the means to do so. So you've got people over on the high end trying to make it easier and more ambitious in its analysis so that someone doesn't have to be as trained to jump into it.
Yeah. That I show my age again. That kind of makes me nervous. If we get to the point.
I was thinking that.
You don't have to have the depth.
I see you did.
There's some hesitation. You'll see that from people when you're talking to customers about it, where they kind of get that like nervous look, like how much of this is going to displace me when eventually it does it without me needing to look at it. And that's not really the intent of it. It's meant to make it more repeatable, not displace a human in the workforce. But it's certainly made it more approachable for someone to enter a materials position in the workforce that might not have been achievable to them without a 6+ year degree in materials science.
Dr. Wu, any thoughts on that from an education perspective?
Good point.
Yes. So, so currently,
Start a fight here.
I'm gonna hide.
so right after I joined UCF a couple years ago, so I realized, there are not manufacturing courses being offered in the department, in the mechanical aerospace engineering department. I was super surprised. I worked at Georgia Tech before, Penn State, Iowa State. They all offer such manufacturing-related courses, either in mechanical aerospace or in industrial engineering. And then I developed a new course called digital manufacturing. So the first year, when I offered this course, about 30 students enrolled. Second year, 100. And then right now, this semester, or not last semester, I was teaching this class, 350 students enrolled in digital manufacturing. So I guess it's really not about no students or American students are really interested in manufacturing. I think, in my opinion, at least based on my experience, it's really about what content you teach and how you teach manufacturing. So a lot of students, I ask them why you enrolled in my digital manufacturing class in comparison with other classes where conventional manufacturing processes will be taught. And I think most of them, the answer is they want to learn more advanced manufacturing processes, more interdisciplinary skills, how automation, mechatronics, AI, computer science can be integrated into manufacturing processes or systems. And also maybe another reason why there are so many students, over 300 students enrolled in my class, is in the first class, I always tell them some stories. For example, I always tell them my first PhD student graduated from my lab, his entry-level salary is $160,000. He graduated from mechanical aerospace engineering, and he is currently working for Honeywell. So that is his first job. So I think this is another way is to really motivate students. You can get decent job, decent salary, even in manufacturing industry. Because some of students, they assume this is really like a blue-collar type of industry where they are not able to really get a very high salary, which is not true. It really depends on what skills you have, right? So if you work in relatively lower-end manufacturing, it might be true, but if you work in a higher-end manufacturing, it's different. So I think that's one of the issues about the curriculum design. So maybe most of the universities probably need to think about how they redesign their curriculum on manufacturing, providing students with more solid backgrounds. So in addition to very conventional mechanical topics, subject areas such as fluids, thermal, heat transfer, or solid mechanics. Manufacturing is more interdisciplinary, in my opinion, which require all the knowledge from all these subjects. This is about curriculum redesign development. Another thing is about how we teach manufacturing. So rather than teaching manufacturing in a regular classroom environment using slides, so these slides actually will put those students fall asleep easily. So in my opinion, using something new teaching philosophy or theories in education might help professors to teach manufacturing in a different way. One idea is to utilize something called project-based learning. So typically, I teach students using slides maybe for the first half of the semester. And then the second half of the semester, actually, I will design some hands-on projects and allow students to form a group and solve those hands-on, sometimes even real-world problems in a group as a course project, which actually will occupy sometimes even 50% of their final grade. So in this case, students will actually figure out how to apply the knowledge they learned or the materials I taught to solve real-world problems. Instead of I just feed them with some knowledge and I let them read the slides and learn everything by themselves without knowing how to use those knowledge. So this is the second aspect. The first one is redesign the curriculum and really develop new courses similar to digital manufacturing or advanced manufacturing So covering actually a broader area of manufacturing industry. And then actually developing new teaching methods to teach manufacturing. These are my
Dazhong.
thoughts.
Thank you. Appreciate that. I'm gonna transition into some of the audience questions. If you haven't already got your questions up there or upvoted, I'll go down some of the lists. So this is kind of, we'll see if we have the right expertise on stage. So just volunteer. Karen, you might be somebody who has some knowledge in this area. I'm not really sure. It's a broad question. What is the outlook for composite materials? Any thoughts? No?
Yeah, no, so composites
Yeah.
have a lot of potential, as do metals, as do ceramics.
Yeah.
I think that the true materials solution is what's the right application.
Yeah.
As we are seeing more blended wing body and truss brace wing, high aspect ratio, long, thin wings, the composites have the strength to weight ratio, but more the stiffness that is really critical for enabling some of those geometries. And so I think that as we're seeing different geometries coming into for future applications where we talk about grain aviation. Operational side, there's a lot of composite because of the efficiencies on the operation. But I would also say that composites are not or should not replace metals in every application, because there are some places where metals still make sense from a manufacturing rate, from a recyclability, and so that green manufacturing, at the end of life, that's where we've got some work to do on composites. At the end of life, what do we do with that composite material after we can't recycle it as easily as we can an aluminum airframe? And so, but there are a lot of applications for composites in space. The stiffness is critical, and so as long as it's not eaten away by the atomic oxygen and the space radiation environment, there's a lot of value in composites, because the stiffness there's not gravity, so stiffness is really what drives your structures. And there are things that you can do to tailor composites for a zero coefficient of thermal expansion, which is a big deal when you're talking about these gossamer structures that go between sun and shade. You've got huge differences in temperature. And so there, if you can tailor your coefficient of thermal expansion, which composites are more tailorable in that way. So I think that from an organic, polymeric composite, there's a lot of applications, and we continue to see the adoption and the improvement of manufacturing rates. BMW is stamping hoods and body panels out of composites. And so there are high rate manufacturing approaches that are available out there. So I think that composites, we just want to be cognizant of what's the end application and what are the needs. But yeah, I think that there's a lot of potential out there for composites and continued development, but don't forget your metals brethren, don't forget your ceramics, because they're out there too.
Others?
Maybe I can share a little bit thoughts on this. So I think I've seen some very recent studies where people develop composite-based structure batteries. So basically people develop 3D printed composites. But these composites actually can also generate power, electricity. One of the potential applications is you can use such composite structural batteries to build the frame of a drone. So imagine in the future, maybe this won't probably happen very, very soon, but let's say 10 years down the road, you can imagine some drones flying in the air does not have a battery, but the frame or the structure itself generate electricity to power the drones. Yeah, I think this is probably is very promising based on some of the fundamental research I've seen. Yeah, this is some interesting studies I saw.
Great. If I can jump over to you, Jay. A question came in from the audience on what are the robotic technologies that have the greatest impact on accelerating integration and assembly of subsystems and systems and are ready to transition to industry. Do you have any insights on that?
Well, I think what's been going on with robotics and manufacturing, there were robots in automotive manufacturing plants in the 1960s. So they've been around a long time, but about 7-8 years ago, there was an inflection point when artificial intelligence really became the key technology at the end of the robot arm, at the end effector. And it's really become remarkable what robots can do. They can see, feel, sense, lots of different things. And I think that's a real key aspect, and that's changing every day. And the use of generative AI to program a robot, it's making it a lot faster. The robotic industry is, it's, I don't know if it's weird or if it's sad, but everybody still uses a proprietary operating system. It's not where desktop computers are right now. But, the use of generative AI to kind of cut through that, I think has been a big difference maker in adoption. There's also a lot of help out there through, talking about us, public-private partnership, but through other things, programs that are funded by the Department of Commerce and NIST, ways to get robots installed into small companies, which is a big barrier. But those are some of the things that are happening every day. And I think the use of robots is really starting to accelerate.
Any other observations?
Yeah, I would echo that for sure. ZEISS, the company I work for, uses robotics quite a bit in some of our implementations, less on the microscopy side and more on the sensor side, specifically our 3D optical sensors. We're using robotics both for part automation, for loading and unloading, to do large batches of components to help accelerate the speed of inspection, but also enabling it to attach a sensor to the end of a robot to do much larger components too. Things as large as plane fuselages, where you've got 1 or 2 robots on tracks that are moving a 3D sensor around, detecting and looking for defects and abnormalities and things that are varying from a nominal dimension that's supposed to be there.
Appreciate it. We're kind of rounding out towards our time. We're going to do a little bit of a speed round, a minute or two a piece. If you can just take each of the panel members, take a moment to reflect on any of the common themes you've observed across these issues, or if there's something you kind of wanted to impart on the audience before we wrap this up, and we'll do this in reverse order. So, Dazhong, Dr. Wu, would you like to start?
Okay, so if one take-home message you want to take from me is, I think it's about AI-driven, affordable, scalable part qualification and certification. I think this is a billion-dollar industry and problems. So if you are really interested in a startup company, maybe this is one of the ideas or problems you want to solve.
Great, thank you.
I think manufacturing is a multidisciplinary challenge. And really understanding the aerodynamics, the applications, the structures, and the materials. Manufacturing is what brings all of that together. And manufacturing done well can enable operational systems that will meet the requirements and improve your efficiencies. ILIDs in the industry, they call them the ILIDs. They're really hard to measure, but they are what drive. That's what drives the whole operational world. So being aware of those is important.
Thank you, Karen. Okay.
Just 2 quick things. I'd look to your manufacturing innovation institutes to help you solve problems and leverage funding to get into some of the more complex things. And encourage young people to pursue jobs in manufacturing. Sorry, Professor.
And I'll kind of add that materials inspection and materials improvement are kind of a real symbiotic relationship. Advancements in materials have driven us to create new innovations to help you inspect them faster, and vice versa. I think some of the advancements in microscopy and image analysis have also made it a lot easier to detect things in samples that maybe were difficult to detect in the past. So kind of one improves the other and vice versa. So it's great to get to interact with our customers and industry and researchers to not only help improve what they're doing, but have their innovations help us innovate as well.
Thanks, Trevor. Well, it's been a great panel. I really appreciate all the insights coming from a pretty diverse panel, coming with some different perspectives. From the Air Force side, from where I sit, very excited to hear the thinking that's going in and through the community here. I mentioned it in the beginning. We love to focus on the exquisite, on the challenges, on the hard problems. Part of what we need to focus on right now is also just the affordability and the scalability and the manufacturing rates, which is why we touched on some of them. We started out with additive manufacturing, and it is kind of that thing that a lot of folks that might not understand the technical underpinnings of what it would take to do qualification and stuff think that might be the easy button. So it's something that we are struggling with in my organization, is trying to help lead the community in a way that we can, start biting off bites of this apple and getting some of those, maybe it's some of the more understood metal additive, applications first and really ring them through. Another one is just how to do distributed manufacturing. One question came in about what we do for digital engineering and such, and I thought I would just touch on that because I think a big part of the speed for manufacturing is designing for that speed, designing for the manufacturability, and it's critical to do that ever more and more into a digital engineering environment, and one where we have some common standards and things that we can share, which then might enable more distributed manufacturing across the entire ecosphere, opening up additional, suppliers and such. So just kind of some reflection thoughts as I was sitting here listening to the awesome input from the panel. We have just enough time for my last joke. Anybody? Last joke? Yeah, I only have 2 jokes. One is materials and manufacturing, and you already got that one. So this one's kind of from my IT aged background. So I'll just do it real quick. So we got a mechanical engineer, an electrical engineer, and a computer engineer in a car. All right, they're going down the. You can just leave if you don't want my joke. Going cross country, and the car breaks down. Mechanical engineer first up, right? I'm mechanical engineering. He's like, I got it. Probably the drivetrain, transmission, checks out the whole vehicle, can't find anything wrong. Electrical engineer's like, even check the fuses. It's like, it's probably just a fuse, checks out the dash, puts in the little, thing, no flags on the electrical system. Computer engineer's like, come on. Just everybody get out of the car, we'll get back in and see if it works. That's it. Thank you for joining us.